Out of the elements in the soil, water, air, and the energy of sunlight, nature produces an almost infinite variety of plants. Plants that supply us with food. Plants that provide the raw material for our clothing. Plants from which are fashioned innumerable necessities and luxuries. All this organic or living material is produced by nature out of air, water, and the soil. A tree is a good example of this synthesis of natural substances. From the atmosphere, it takes carbon and oxygen in the form of carbon dioxide. Then, from the soil, it takes water and such elements as nitrogen, potassium, and phosphorus. With the aid of sunlight, nature combines these elements to make the tree. Although this tree has its own particular structure, its basic elements are essentially the same as in all species of plants. The wood of the tree is made up of cellulose fibers held together tightly or bonded by natural resins. For centuries, man has taken this natural product from the forests and used it practically unchanged. By a number of operations, cutting to size, sawing, planing, machining, and shaping, innumerable useful products have been made, such as this wooden radio cabinet, which in finished form is still like all wood, composed of cellulose fibers bonded by natural resins. But many products formerly made of wood or other materials can now be made with greater ease and improved design out of relatively new materials we familiarly call plastics. The plastic material of this radio cabinet is also composed of cellulose fibers, but the fibers are bonded by a synthetic resin, a resin made by man. Like all plastics, the material of this cabinet, which is a phenolic compound, is made from substances found in nature. Just as the tree takes elements from air, water, and the soil, and with the aid of sunlight grows and develops, so to make the phenolic plastic, we also take elements from nature. For example, one method of making phenolic plastic utilizes coal, air, and water. In this method, we begin by heating and refining the coal to get a substance called phenol. Then, by burning the coal, it combines with oxygen from the air to form another derivative, carbon monoxide. By sending an electric current through the water, we can separate hydrogen from it. Combining the carbon monoxide with the hydrogen under suitable conditions will produce formaldehyde. Finally, by combining the phenol with the formaldehyde, we produce the phenolic plastic. In commercial practice, mixing the phenol and formaldehyde is done in huge steam-jacketed kettles under carefully controlled conditions of time, pressure, and temperature. Here we see the complicated process on a laboratory scale, where the steps can be clearly observed. A measured amount of phenol crystals is placed in a flask. Two-thirds as much formaldehyde is then added, and the mixture is swirled about to help dissolve the phenol. A very few drops of sulfuric acid are added to start what is known as an exothermic reaction. Further mixing and heating will help induce the chemical reaction. As soon as the flask clouds with steam, indicating that the mixture has been heated sufficiently, it is attached to a reflex condenser, through which cool water is constantly circulating. The flask is lowered into an oil bath. To which heat is applied. The oil bath must be maintained at a constant temperature of 110 degrees centigrade for 1 hour. In an hour, the heat is removed. The flask is taken out of the oil bath. It is also detached from the reflex condenser. Then, to draw off the water which is collected on the surface during the reaction, a suction line is attached to the flask. The mixture is kept in this vacuum as long as is necessary to remove the moisture. The compound which now remains in the flask is phenol formaldehyde resin. This compound is poured into a mortar and allowed to harden. As soon as the resin begins to solidify, coloring pigment is added to give the desired color. And the mixture is ground together so that it's uniform. Wood flour is also added to give the material the exact properties required. The resulting mixture is screened to provide a phenolic powder which is just right for the radio cabinet. Strong enough, the right color, proper heat stability, and so on. The cabinet is to be molded in a hydraulic press. The material is placed in a heated steel mold, and the mold is closed so that heat and pressure soften the compound and make it flow into the shape of the mold. Continued heat and pressure permanently harden or set the material. The molded cabinet can then be finished for use by touching up the line where the die closed and painting in the molded insignia. Thus, from the raw materials of nature has been synthesized a new material, a phenolic plastic, out of which this radio cabinet has been molded. The transparent face over the dial is also plastic, but this one is called polystyrene, one of several plastics well suited for such a part. One of the ways of making polystyrene is from coal and natural gas. By heating the coal, we can produce benzene. By heating and refining natural gas, we can produce ethylene. When ethylene and benzene are combined and heated under certain conditions, we can produce first styrene, and then by further processing, the plastic material polystyrene. This time, polystyrene is used with no dye or fillers because the dial must be transparent. The dial face is to be cut to size and shaped from sheets manufactured by another process known as extrusion. Here the material is placed in a hopper. Then a continuous screw forces it into the heating chamber. Heat and pressure soften the material, and it is forced out through the die opening in hot plastic form. The cabinet and dial face of this radio are only two of the many plastics now in use, but they illustrate the two basic categories of all plastics: thermosetting and thermoplastic. A thermoplastic material such as this sheet, which is the same polystyrene from which the dial face was made, originally was hardened by cooling and can be softened by heat. It can then be reshaped and will harden again by cooling. A thermosetting material which hardened through chemical changes under heat remains as rigid as ever. It may char, but it cannot be softened or melted. Once formed and hardened, it can never be softened and reshaped. Thermosetting materials are hardened by a process that can be compared to the making of a waffle, which, once it is set under heat, cannot be melted or reshaped. So we call them thermosetting or hot set materials. Thermoplastic materials can be compared to wax or paraffin, which hardens by cooling. They can be softened by heat and reshaped, and will then harden again by cooling. Thermoplastic materials are often called cold set compounds. Now, just as the plastic materials of the radio cabinet and dial face can be made from air, water, coal, and natural gas, much as a tree grows by using the elements in air, water, and the soil, so all plastics are made from substances found in nature. Different substances and combinations being used to produce plastics with different properties for varied uses, just as nature produces infinite varieties of plants from basic elements. In every case, heat, catalysts, and other chemical processes are involved, and dyes or pigments can be added, as well as fillers and plasticizers, to produce materials of just the particular properties we want, in powder form or in rods, tubes, and sheets, or as liquids, to be manufactured into a variety of products. Thermosetting spinning buckets that resist acids and chemicals. Thermosetting noiseless gears of great strength and wear resistance. And having good electrical insulation properties for heavy-duty electrical operation. And heat resistance, as well as excellent decorative properties and resistance to stains. Thermoplastic bottles that are used for acids which attack glass. Thermoplastic products of considerable flexibility. And a variety of thermoplastic products in many beautiful colors. Thus, out of plastic materials are manufactured countless finished products. From the clothing we wear and the buttons on our clothes to the intricate parts in our communications networks, power plants, ships, automobiles, airplanes, and railroads. All these and thousands of other items, small and large, that enrich our way of life, involve the use of plastic materials of one kind or another. And thousands more are constantly being planned and developed.